We have here another problem involving the first law. So it says the tangential force acting on the cutting tool of a lathe when turning a metallic workpiece of 80 mm diameter is 180 newtons. So I am assuming that all of you have been to a workshop and you have done turning operations on a lathe. You know what a lathe machine is. So you have, for example, a rod which you want to turn. The rod is fitted on the chuck and it's rotating, and you have a cutting tool which is going to be somewhere like this, and this is rotating and this is cutting and progressing. So what we see is that the tangential force because of this, let's say this is the cutting tool, tangential force because of this cutting tool is 180 newtons. So the force is 180 newtons. So we have a metallic workpiece whose diameter is given. So let's maybe draw a metallic workpiece. So the diameter of this workpiece is given as 80 mm. So which means that the radius of the workpiece is 40 mm. Let me convert that into SI units. We have that. So after 8 minutes of turning, the internal energy of the workpiece and chips has increased by 80 kilojoules. So the time for this process is 8 minutes. That's 8 into 60 or 80 seconds. What it says is that the internal energy of the workpiece and chips has increased. So when you turn this, you have like say a cutting tool over here and you're turning it. You're going to remove some amount of material which are the chips. So the internal energy change for both the workpiece, whatever is left, plus the chips which are generated is given. So let us consider both this workpiece plus the chips as our system. So the system is initially this workpiece or the rod. Finally, it is the rod which has been machined. So let's say this amount of material has been removed finally, and whatever here is now the chips. It will become as chips. So we have finally it is the machined rod plus whatever material was removed during the machining. So the mass of this and the mass of this are the same. So there is no change in the mass if you consider both of them together. And the change in internal energy is given as 80 kilojoules. So I am going to write that here. The frequency of revolution of the workpiece is given as 250 revolutions per minute. So N, the rotational speed is 250 rotations or revolutions per minute. So that's 250 by 60 rotations per second. We are asked to estimate the heat transfer from the workpiece and chips in this time. So what we know is the forces, we know the time for which this force is acting, we know the change in internal energy, and we are asked to find out the heat transfer. So because we know the force is acting, we can calculate the work interaction for this. So I have a force which is acting tangential, which is acting at some distance from the center, and this whole rod is in rotary motion. So I can calculate what will be the cutting torque which is acting on this. So the cutting torque would be given as the force into the distance from the axis, which is like some r. So the force given to us is 180 newtons and the radius is 40 mm. So I have 180 newtons into 40 mm, which is 0.04 meters. 40 mm is 4 centimeters, that's 0.04 meter. So I can find out this torque. which is 7.2 Newton meter. This is the torque which is acting. So, the work done would be the torque into the angular displacement, that's T into theta. So, I can also write this as theta is omega into time, omega is 2 pi times n. So, I have this. So, the work is going to be T into 2 pi n into time. So, I have the torque is to 7.2 Newton meter into 2 pi into, I had the rotational speed in seconds, 250 by 60 revolutions per second, into time was 480 seconds, 8 minutes, 480 seconds. This is revolution per second, this is into second, so those get cancelled out. This has units of Newton meter which will remain. So, I can find out this in Newton meter. Which gives me a value of 90,475. So, that's 90.4 kilojoule. A Newton meter is a joule when you are talking about work. So, that's 90,000 joules, which is 90.4 kilojoule. So, this is the amount of work interaction which is there. I was already given the change in internal energy, which we wrote here as 80 kilojoule. What we see is internal energy increased by 80 kilojoule. So, final minus initial is 80 kilojoule. By delta U, that is generally what we mean, but just to be explicit, we have written that here. So, this change is positive. So, final value is higher than the initial value. So, now again we can write the first law. This is for, of course, a system undergoing a process, and we do not have any changes in potential and kinetic energy. So, we can, instead of du, we can write it like this, and the integrated form of course is this. So, this is 80, we do not know q, we want to find out that, w is 90.4. So, over here when we wrote this expression, we did not write the sign for w, so which we can now look at. So, in this shaft we see that something is doing work on this shaft and removing material. So, work is being done on this substance. Therefore, for this system which consists of this shaft, the work would be negative. So, when we wrote that here, we did not explicitly write this as the sign for it, which we will now do. So, 1 W2 is negative. So, this is minus of minus 90.4 kilojoule. This is also in kilojoule. So, I can find out Q, which in this case is 80 minus 90.4, which is minus 9.6. Sorry, it's 90.4 and 80, so it is actually 10.4. Yeah, minus 10.4 kilojoule. So, again we see that the direction of heat, so the heat is negative, which means there is heat transfer out of this system, which is what we would expect. So, by doing work on this shaft while it is rotating, when trying to remove material, the shaft gets heated, its internal energy increases, but it also, because of its temperature also increases, and then it loses heat to the atmosphere, which in this case has a value of this.